This is the 11th lecture of this course. Let us recall from the last lecture that we have discussed there the notions of linear span of a subset S of a vector space V, and the notions of linear dependence and independence. So, let us recall that what these mean. So, suppose I start with a finite set V1, V2, Vk, a finite subset of V where V plus dot is a vector space. So, then linear span is defined as the all possible linear combination of the elements of S. So, this is I am doing assuming that S is a finite set having k elements. When for general S, when S is not necessarily finite, S is not necessarily finite, then in that case L of S is defined as the collection of all possible finite linear combinations, that is for A we will first pick up finitely many elements for S, and similarly finitely many scalar, and also k is allowed to vary because I am collecting all possible finite linear combinations. So, this is the definition of linear span for any general set, but in this course mostly we will stick to the vector spaces which can be spanned by vector spaces which can be spanned by a finite subset of that. So, this is going to be more relevant to our context. Of course, we will see infinite we will see infinite the subspaces generated by infinite sets too, but as I said more often this is what we will be dealing with. Okay, so we have also discussed several examples of linear span. If you recall that if S is a singleton, if it is a singleton set, possibly a non-zero vector, then its linear span is the line. Okay. So, if I take as I repeat, if I take the non-zero vector in R2, then its linear span is line, and suppose if I take two vectors in R3 looks like this. Suppose this is one vector and this is another vector, then we geometrically we argued that we have seen geometrically that it is actually a plane passing through origin and containing these two vectors, but as I said our argument was geometric because we define lines and planes algebraically by equations. So, given two vectors V and W, so far it is not quite clear that what is going to be the equation of this plane, but as I said let us be happy with this much for the time being. So, later on we will see that how to get the equation of this plane. Anyway, so these are the examples that we have seen. Then we have also seen some other examples. For example, okay. So, for example, for matrices of square matrices of order n, then we see that for let us say for n equal to 2, 0 1 0 0, the linear span of this is nothing but the space of all upper triangular matrices. So, we will also see some other linear span of subsets. So, let us rather look at that. We have also seen for Fn that the following set U and the span of the following set, where EI is the vector having I at 1 at the ith coordinate and 0 elsewhere, the linear span of this is nothing but Fn. So, we have seen all these in the last lecture. So, let us see other subspaces of Fn. So, recall that given a matrix M by n matrix, given a M by n matrix over F, the set of all vectors such that Ax equals to 0. Remember what this means is x, since x is regarded as a tuple. So, while writing Ax, it is automatically assumed that I mean, so the tuple I will view it as a column vector, and then so here it means I am looking for all such external such tuple external protection such that when we view the tuple as a column vector, by multiplying that by A we will get 0. So, this is a subspace of Fn, right. Let us try to see so let us try to see a subset S of this subspace which spans this subspace as well. Okay. So, I repeat, what I am going to do is I will look at a subset S of this whose linear span will be this subspace itself. Okay. So, what is the natural choice for that? Recall that for such a matrix, how do we find all such vectors x such that x is 0? We do it in the following way, that starting from A we reduce it to its row echelon form A prime. Then in the row echelon form, what will we have? We have the following, that there will be some 0 rows, okay, the some 0 rows, and you will have we will have let the first r rows are non-zero. So, this has order m by n. So, we have m minus r possibly 0 rows. So, 0 rows you can simply ignore. So, let us not look at this let us simply ignore this 0 part. So, now you have r non-zero rows. So, each row will contain a pivot. So, let us assume that the row pivot of the first row lies in the column k1, the pivot of the second row lies in the column k2, and similarly the pivot of the rth row lies in the column kr. Okay. So, therefore, now the set of n variables are now grouped in are now divided into two groups. In one group we have the variables xk1 up to xkr, and on the other group we have the rest of the variables. So, so what we do is we define j to be the indexes from 1 up to n other than okay, j to be the indexes. Okay. So, then how do we solve, how do we get all the solutions of this system? That is very easy. Corresponding to each j in j, we assign the value Cj to the value Cj to the variable xj, and also let us assume that for A dash a typical entry is Aij. If we assume the entry is in A dash or Aij, then how do we calculate, how do we compute the after assigning values arbitrary values to the variables in corresponding to this index at j, how do we calculate the values of the other variables, namely xk1 up to xkr? These are done by the following equation: xk1 becomes c 1j okay, I should this a1j cj j in j. Similarly, xkr will be j in j a kj, so sorry arj C j, right. So, remember how do we so okay. So, in fact, we have also seen that any solution must be, any solution of this system x equals to 0 must be of this form. Which form? So, in a typical solution we have, the coordinates corresponding to this j, we will have Cj's, okay, and the coordinates corresponding to k1 k2 kr, we will have this, we will have these quantities, okay. So, as I said, assigning values Cj, arbitrary values Cj to this xj's, we will get a solution like this, and every solution is of course of this form, because these variables are connected. So, the variable x k1 is actually connected to the variables xj, where j lies in j by the in the following equation, by the following equation, right. Similarly, for x j. So, since these variables are connected like this, so certainly the value of x k1 has to be the combination of the values of x j like this. So, that shows these are all the solutions, this all we have seen already. Now, from that idea that assigning arbitrary values to these x j's, we get all the solutions of the system. From that, so do we see a very natural choice of a the natural choice of a subset S of this solution space, whose linear span is the solution space itself? We have a natural choice, right, namely the following. So, remember how we solve, we assign arbitrary values Cj to the xj's. So, corresponding to each j in j, we let Ej to be the solution, which is so I will explain you what the solution is. So, the jth coordinate of Ej will be 1, okay, and the other coordinates j prime belonging to j, but not this, then the j, all such j prime components will be 0. Now, thus the coordinates corresponding to each point in capital J are now given. We are just only left with the coordinates corresponding to k1 k2 kr, and for them we know how to what to put in that coordinate, and simply the k1 coordinate here will be simply using the equation x 1 j, okay, simply x1 j minus a1 j, okay. So, this is going to be the k1 component. Similarly, kr component will be minus a r j, okay. So, what is the solution? So, in the jth position it will have 1, and the other positions corresponding to this corresponding to the other points in capital J, they will be 0, and so we are left with k1 k2 kr, only these many positions. So, on k1 position the coordinate will be a minus a1 j, and similarly in the kr position it will be minus arj, okay. So, corresponding to each j we have such a vector Ej. So, the set that we want to consider, the set that we want to which we will consider is E j, j lies in j, okay. Now, just to show that this S, the linear span of this S is the solution space, what to do? So, how will a typical solution look like? It will look like this, as I have expressed. So, if I want to show that Ls is the is the, so this is what we want to show, like. So, one thing is clear that each element in S lies in this subspace. Okay. So, therefore, any linear combination of these will lie in the subspace. So, thus LS is a subspace of that, that is quite clear. So, now you have to show that any solution can be written as a linear combination of the EJs, and that is actually very easy. How? So, a typical solution will look like this. So, in the ith so corresponding to each j in j you will have Cj. Okay. So, that motivates us to consider, like in this vector, so I suppose I want to get this solution as a combination of this. So, so then what are the scalars to be chosen? You see we have Cj here. So, that immediately motivates us that the following should work, right, the following should work, where Cj is the j's here, and that is very easy to see why. So, in this, so this is going to be a tuple, right. So, in that tuple let us see what are its coordinates. So, corresponding to if you fix a j in j, then what is going to be its jth coordinate? So, for that j we have a term Cj Ej. So, if you multiply Ej by Cj, then at the jth coordinate you will have Cj, and for other j prime the jth coordinate is simply 0, right, the way we have defined the jth coordinate is simply 0. So, therefore, the jth coordinate of this final tuple will only come from the jth coordinate of Ej, right. So, what is the jth coordinate of Ej? It is Cj. So, corresponding to each j we see that its jth coordinate is Ej. Now, only we have to make sure of, now only we have to show that the other coordinates are given by this. So, I should have written here the kth coordinate is given by this equation. So, minus a I a a1 j Cj, right. Similarly, kr is the coordinate is a r j Cj. So, now that is very easy to see. So, now we will see what is the k1 coordinate of this tuple. So, the k1 coordinate of this tuple will come from the k1 coordinate of each of these tuples from each of these Ej's, and there's then we have to add them up, right. The k1 coordinate of this final tuple will be the sum of the k1 coordinate of each of these tuples. So, what is the k1 coordinate of corresponding to a j? What is the k1 coordinate of Ej? The k1 coordinate of Ej is minus a1j. So, when you multiply that by Cj, it will be minus a1j times Cj. So, when you sum them up, it will be minus a1j Cj j in j. This is precisely what you have here, and there is nothing special with k1. This goes for any k1 up to kr. So, thus all the solutions are, so the any solution is actually a linear combination of the Ej's. Okay. Okay. Let us look at some other examples as well. So, yeah, fine. So, so for this space we have yeah, next. So, let us take the space of all matrices having trace 0. This is a subspace of M and F. Okay. Then how should we? So, what should be the can I find a set such the whose, can I find a subset of that whose span is going to be the subspace itself? I repeat. So, yeah, so let us make it rather simple instead of getting into that. So, no, let us first stick to this, then we will go ahead. So, what is a subspace? What is a space set that can span the subspace? So, for simplicity, if you take 2, so a typical matrix will look like A B A minus A, right. So, what does this just for let us say for n equal to 2. So, what should be the subspace? So, is not this the following that 1 minus 1 0 0 and 0 1 0 0 and 0 1 0 0, right. So, any typical vector this can be written as a linear combination of them. So, for n equal to 2, this is the set that spans the space of all trace 0 matrices. Okay. So, for now from this you have idea that how to get a spanning set of that from how to get a spanning set of that. By a spanning set I means a spanning set of a subspace I means the it is a subset S or such that the LS is the given subspace W. So, for general n you know how to get a spanning set of that. Okay. Let us see some more things, some more examples and instances of linear span. Geometrically we let us again come to this example. If we are given two vectors V and W in R3, then what is the span of this? We see that if V and W, if one of them is linear scalar multiple of the other, then the linear span will be, I mean if V W is a scalar multiple of that, then the linear span of V comma W is same as the linear span of V, which is geometrically realized at a line passing through origin, otherwise it will be a plane. That is what we have seen. Now, the point is, how will I understand that whether these, whether given two vectors, whether V is a scalar multiple of W or W is a scalar multiple of V, how am I going to understand? Suppose I have been given the coordinates V1, let V equal to V1, V2, V3, W equal to W1, W2, W3. So, the exercise is to find a relation among this V1 Vi's and Wj's, find a relation involving Vi's and Wj's that will you determine whether W and V are one is a scalar multiple of the other or not. Okay. Fine. So, I am leaving that as an exercise, this is a simple exercise. Now, we will rather look for something even more general. So again let us stick to Rn or Fn, does not matter. Okay. Suppose I have been given m vectors, so k vectors V1, V2, Vk, let this be. So, Ls is going to be all possible linear combinations of these vectors. So, given V1, V2, Vk, how do we understand, the question is how do we understand whether a given vector, let us say x, or if I write let us say a given vector W will lie in the span of this. How will I understand? Do we have a way? Of course, by definition you might say we have if we can find alpha naught to alpha k such that this happens. But how do we know that we can will be able to find or not? Do we have a way which will tell me that whether this such alpha naught to alpha k exists or not? Do we have a way in terms of what we have developed earlier? In terms of that, do we have a method to determine whether we have alpha naught to alpha k or not? So, for that let us observe the following, that suppose you have been given a matrix A, some m by n matrix whose entries let us say let A Aij, and when you multiply this matrix, let us say by some column vector, let us say x1 up to xn, then what exactly happens? So, in one hand you have the first column A1, A11, A21, A1n, sorry AM1. The general ith column would be A1j, A2j, AMJ, A1n, A2n, AMn, and when you multiply that by x1 up to xn, what exactly happens? What is the, if you remember how we multiply is, so A1 is for the first row, A1 is being multiplied by x1, A2 is being multiplied by x2, and then we add them up. Now, for the second row, A1 is being multiplied with x1 is being multiplied with A21 and the usual one. So, what I am saying that, isn't it the following that the whole column A11 up to AM1 x1 plus, so the whole first column is going to be isn't, what I am saying is, isn't the product is same as the whole first column is being multiplied by the x1, the whole second column is being multiplied by the say x2, and similarly the whole mth column is being multiplied by a n, right. It is easy to see. So, basically that means when you multiply a matrix by a column vector from the right, then what is actually happening that we are taking the combinations of the columns of the given matrix by the column vector, by the entries of the column vector. Okay. So, does not that show us something for the question that I have just asked? It is very easy to see that what we do is, so V1 is a vector in Fn, so it will have n coordinates, right. So, let us do that. So, let the coordinates, so we will write down the coordinates along the column. So, V1 we write V11, okay, for simplicity let us what we should do is, okay, so V11, V21, and then we write Vn1, okay, Vn1. So, these are the, so V1 is nothing but V11, V21, Vn1. Okay. Similarly, for any I we can do this, yeah, V1I, V2I, Vni. So, we will put the vectors, so these are vectors along the columns of a matrix. Okay. So, we will form a matrix whose ith column will be the vector Vi. Okay. Now, and let the column, let the entries of W1 are W1 up to Wn. Okay. Now, if this happens, that means alpha 1 up to alpha k is a solution to this system. Okay. Similarly, if alpha 1 up to alpha k is a solution of this system, that is the system, if we say this matrix as B, and then if we call this as for the time being something, if you say y, so Bx equals to y, whenever we have a solution of this system, then that solution shows that this vector w can be expressed as a linear sum combination of that. So, therefore, given a set, its linear span is precisely those vectors for which the system admits a solution. So, thus the problem of determining the span actually comes down to, so the problem of determining whether a given vector lies in the span, that actually reduces in an equivalent way in fact to the problem of solving a system of linear equations. Okay. And for solving such a system, we have already developed methods, namely reduce it to row echelon form, then we can do it. So, that is the way, that is the practical way of determining whether something lies in the span or not. Okay, fine. So, we have thus we have seen the examples of several examples of linear spans. We look for one more example, then we will perhaps go ahead. So, let us remember that f t is the, if t is a variable, if t is a variable, then the subset 1 t t square subset of f t. So, this is an infinite set. As I said, mostly we will stick to S, mostly we will be dealing with finite sets, mostly dealing with the case when S is finite, but we will encounter two such instances where S is not finite, namely this is one. So, the question is, what is the linear span of S? What is the linear span of S? It is easy to see that at any polynomial here will actually be a linear combination of finitely elements from the set S. Therefore, Ls is nothing but f t. And if you remember, we in fact viewed that from a much more general perspective, namely for any x not equal to mt, we consider the set of all functions from x to f. So, there we can consider the following set, namely the Ex, where what was Ex? Ex was the function from x to f, so that Ex y is 1 if y equal to x, 0 otherwise. So, what was Lx? Lx was the functions typically which looks like so Lx was namely all functions which vanish identically outside a finite set. So, as I said earlier that we will rather write them by simply with simplified notations such that x 1 up to x k lie in x, alpha 1 up to alpha k lie in f, and k integer. Okay. So, let us make some for again for simplicity, let us make some further convention that so the convention will be made in view of this, that this as I explained earlier that this representation is very handy and useful while making manipulating elements from f x. So, what we do is, so if you remember what is this function, this is function, this all summation, this formal sum summation E x x I is nothing but the actual linear combination. Okay. This is what we have seen. So, what we will do now is a very obvious thing, we will identify x to the corresponding E x. By identifying I mean I do not distinguish between x and E x. Okay. So, therefore, once we do that, so let us also see one thing, then this function E x, if I want to express E x by such a formal expression, what will be that? So, E x is the function that takes 1 at x and 0 elsewhere. So, E x should be written as 1 times x. So, I mean if we used to if we stick to this formal notation, so this is my E x, and we will from now on we will simply identify x and 1 times E x, that is will not make any distinction between them. So, once we will not make any distinction between them. So, that means the set x is being identified with this set S, okay, and the f x is spanned by, so f x is spanned by S. Right now I am saying x and S are identified. So, therefore, we can simply say from now on that f x is spanned by x itself. So, this is just to make terminology simple. So, from now on we will simply say that the vector fx is actually spanned by the set x. So, let me repeat, this is this terminology we adopted after an identification for the sake of simplification in notation and terminology. I mean, otherwise to begin with x, so x is spanning something that does not make any sense, because x may not be a subset of any vector space, right. So, after identification now we can simply say that this is spanned by x. Okay. So, we have seen this, and okay, we can let me give one more example that is also very interesting and important actually. So, given any vector space, its span, so given any vector space, so what may happen that like two different subsets can span the same vector, can span the same subspace. So, it is nothing new. For example, we have seen the earlier example that if one of them is a scalar multiple of the other, then this is a quite obvious thing, but it may also so happen that the two subsets, they have no element in common, they have hardly an element in common. Even then they can span the same subspace. So, let me give two examples for that. So, for example, E1, E2, En spans the whole, E1, E2, En spans the whole Fn, right. We want to get another, let us say we want to get another subspace, another subset of, we want to get another subset S, which also spans the same Fn. So, how to get that? So, if you remember that at any set V1, V2, Vk will span Fn if for, so exactly what we have just discussed a few minutes back, if for every y in Rn the matrix which is formed by so this x equals to y has solution, right. So, remember this means this stands for the matrix whose columns are V1, V2, Vk. Okay. So, S will span Fn if for every yn there is a solution, if for every yn there is a solution. So, does that simply, so in view of that we can immediately conclude that this, when does that happen, that for every y we have a solution, when does that happen? We can immediately see it will happen, I mean later on we will show you sufficient too. So, it will happen if the matrix V1, V2, Vk happens to be an invertible matrix, right, of order n. So, that shows for any set of vectors such that any set of vectors in Fn such that the matrix formed by these vectors is invertible, then the span will also be Fn. So, thus you choose whatever invertible matrix of order n you wish, then you can see the, so again let me repeat, you choose whatever invertible matrix you wish of order square order n. So, each look at its column. So, any column of that invertible matrix, so when you arrange it in the corresponding tuple, so it will be a vector in Fn. So, corresponding to any such, all such columns you will have n such vectors, and that set of n vectors will span Fn. So, that is what we can conclude. So, that shows that we can actually have plenty of different spanning sets of Fn. Let me give one example for infinite case. So, we will will for simplicity we will give an different basis of sorry, we will give a different spanning space set of this polynomial ring. But before that, let me also remind you that this f x, so what is f x? F x, which I say that spanned by x, f x is the actually the all functions which vanish finite beyond a finite subset. So, f x is not, f x cannot be the whole C x, right. F x is always the proper, f x is always a proper subspace of that if x is infinite. Okay. If x is infinite, then f x cannot be a proper f x cannot be a cannot be equal to C x f. Okay, now let us come to this point. X is, so if x is infinite, this is always proper. So, yeah. Okay. And the what I have just rubbed, the converse is also trivial. Anyway, so let us come to here. So, S is a spanning set. Now, what I am saying is, what you do, you first start with any, let us say any point in F, or let us say fix any alpha in F, non-zero alpha possibly. Then what you do is you consider this set alpha, t minus alpha, t minus alpha square, all non-negative powers of t minus positive powers of t minus alpha. Okay. Or here also you do not need to choose anything, any alpha. So, what you can do is, so you first choose any alpha non-zero and then you fix any beta. So, yeah. So, yeah, that is the rather the more general one. So, you fix any alpha non-zero first and then you choose any beta, then then consider S prime to be this. The question is what is S prime, a linear span of S prime. So, using division algorithm repeatedly, because starting with if f is a polynomial in T, you can first apply the division algorithm on that. Okay. So, applying division algorithm, so then you will have some g plus some, there will be some constant, right, some constant, let us say some gamma, and then you can express gamma by if gamma is 0, then you do not have anything to do, you can simply write gamma equal to alpha times 0. Otherwise, what you can do is you can simply write, okay. Now, for g, the degree of g is less, and then you further apply division algorithm, then so that g will be become t minus beta times some g prime something. So, thus applying division algorithm, you will see that any polynomial is a linear combination of this as well. That shows us the this is also a spanning set. So, we can have, so for through these two examples we can the point that I wanted to make is we can have plenty of sets who do not have at all, who hardly have any member in common, okay, but still they can span the same subspace. Okay. So, enough with linear span. Let us come let us look at come to these notions linear dependence and independence. We will first recall the definition, then we will go for examples. So, for V1, V2, Vk, let us we have defined that for finite sets only, subsets only. So, if this is a finite subset of a vector space V, we say that this is linearly dependent if there is a Vi which can be written as a linear combination of the rest Vj's, right. If there is a Vi which can be written as a linear combination of the rest of the Vj's. So, is linearly dependent if there exists I such that V I is a linear combination of V j's for j not equal to I. Okay. Or equivalently, we can have there exist scalars alpha 1 up to alpha k such that at least one of them non-zero, but okay. So, another definition in fact which we have been motivated to begin in the beginning in the last lecture is the another equivalent one. There exists a proper subset of S such that whose linear span is same as that of S. Okay. And we say a okay. So, this is how we define the general, that is how we define the linear dependence of a finite set. Now, it is also legitimate to ask what happens if S is arbitrary. For that it is quite easy. So, the same thing goes that any arbitrary set. So, if S is arbitrary, then S is said to be linearly dependent if there is if it admits a linearly dependent finite subset. So, the definition goes as follows in turn that for finite sets we define there is notion of linear dependence. For a general set the definition is made in terms of finite sets, in terms of finite sets containing finite subsets containing in that. Okay, so, or equivalently you can say that if there is a linear combination, a finite linear combination of elements from S which becomes 0, but one of its coefficients will be non-zero if there is such a finite linear combination. Okay. And then also this also goes if there it admits a proper subset whose linear span is also same as that. So, that means yeah. So, these are equivalent because when you consider proper subset the point of A is that this proper one misses, then that means that point is expressible linear as a linear combination in terms of the vectors lying in S prime, that leads to a linear combination whose exactly one of the coefficients will be 1 and rest it does not matter what are then the rest, but the whole combination becomes 0. Anyway, then we have also defined that a subset, a finite set will be called linearly independent if it is not linearly dependent. So, linearly independent means it is not linearly dependent. Okay. So, therefore, the linear independence for an arbitrary set goes exactly in this way, that is we say that the set is linearly independent if it is not linearly dependent. Okay. So, therefore, we have the following: S, an arbitrary set, is linearly independent if so again linearly independent means not linearly dependent. So, that means it will have a if its every finite subset is linearly independent, equivalently there exist finitely many points in S. So, if equivalently if for every finitely many points, so let me again repeat. So, what I want to make is linearly independent if and only if for every k and every choice of k points from S and every choice of k scalars, the following happens, that if the combination becomes 0, then each alpha I will be 0. Okay? Each alpha I will be 0. So, I repeat what this means. So, this means that is every finite subset is going to be linearly independent. So, equivalently if you choose any finitely many points and make any linear combination out of that, if the combination vanishes, then none of its coefficients is allowed to be non-zero. Okay? And then equivalently it does not admit a proper subset whose linear span is same as RS. It does not have proper subspace. So, these are just you see the negations of, because the linear independence has been defined as the opposite notion of linear dependence. So, its equivalent criteria, all the equivalent criteria are basically the negation of the opposite of the equivalent criteria for linear dependence. Okay. So, let us see some examples of linear dependence and independence. So, we just quickly go through the examples. For example, the sets which we have already worked with in the earlier examples. For example, let us start with the simplest one, E1 to En Fn. So, is that linearly dependent or independent? That is very easy to see. So, any combination of that. So, I have already said that while checking something is linearly independent. So, it will be more so the negation of this will be more useful, that is we will see if some combination becomes 0, then it has to all coefficients are to be 0. So, this is the one which is going to be more useful quite often, more often in fact, but yeah, but even then there could be other instances where the other ones might be more evident. Okay, so how will a typical combination? So, what is this? As a tuple, this is nothing but alpha naught to alpha n. So, if this is 0, then each alpha I has to be 0. So, this set is linearly independent. Okay. So, what about other spanning subsets of Fn? Fine. So, we have already argued that if V1, V2, Vn is a subset of n vectors of Fn, so that the matrix is invertible. Okay. Then if so, then it is guaranteed that this set is going to be a basis for, sorry, this set is going to be a linear span, so this set is going to be a spanning set of Fn, that is quite clear. So, let us work with that. So, we see that for such a spanning set whether this is linearly independent or not, and that is also quite easy to see. In fact, for any given subset, this holds in general, if we are given a subset of, not k may not be equal to n, a subset of Fn, then V1, V2, Vk is linearly independent, means if and only if each alpha is 0, right. This is what the definition says. Now, if you remember how we obtain this is what we obtain as this n cross k matrix. So, this is linearly independent if and only if this the following system has only trivial solution, right, because if it has a non-trivial solution, then we will get a combination which is 0, but one coefficient is non-zero. So, for a given set of vectors in Fn, it is rather we have a method to check whether that set is linearly independent or dependent. How do we do it? We convert that into the following homogeneous system of equations. Okay. If it is if we can see that that has only trivial solution, then it will be linearly independent. So, in particular when k is n and this matrix is invertible, then this system has invertible solution, only trivial solution, right. So, that means if this matrix is invertible, then this corresponding set will be linearly independent. Okay. As I said, if this matrix is linearly independent, sorry, if this matrix is invertible, then the corresponding set will be linearly independent. Okay. Now, the question is, can we have, like we have a criteria how to, at least for subsets of Rn, how to check the subset is linearly independent. We have a criteria for that, okay, and that criteria tells us if this is an invertible matrix, then it is an invertible matrix, then already we have seen that spans the whole Fn in one hand, and now we have seen that is invertible, that's linear, that subset is linearly independent as well. Okay. But here an interesting question remains open. What it says is that if this matrix is not invertible, then can it span whole Fn, right. We have talked about if the matrix is invertible, then it will span the whole Fn. The question is what happens if this is not invertible, right. So, we have already talked about that for while dealing with system of linear equations, that for a square matrix it is invertible if and only if there is the system has a unique solution, namely the only trivial solution. So, if this is not invertible, then certainly the system will have a non-zero solution, that will system will have a non-trivial solution. So, okay, so what was the question I was talking about? So, the question was regarding spanning. So, if we call this matrix as A is a square matrix, the following things are invertible, that A is invertible, then Ax equals to 0 has always trivial solution, and the thing is for every B Ax equals to B has a unique solution. Okay. So, the question that remains open here, suppose this A is not invertible, that means there can be some B for which either the system does not have a solution or the system will have two different solutions, Ax1 equal to b equal to Ax2, okay, where x1 not equal to x2. So, they either no solution or two solutions. Now, in order to settle that whether if this is not invertible, then whether this can span, whether that can span the whole Fn or not, that part I am for the timing leaving that as an exercise to you. So, in order to show that it does not span, if you want to show that it does not span, then you have to find a B such that the system does not have any solution at all. Okay. So, I think with that I will finish this lecture. Thank you.